Okay, so before we start, again, a few announcements that again, your homework one is due this Friday, September 1st, before the class starts. Also, please note that the lab one documents have been uploaded on your Canvas. So this lab one is just about finding input and output resistances for a network, and mostly for a passive network, something what we already have seen in the past few lectures. So what you will be required to do is to find out the Thevenin and Norton equivalent resistances for certain passive resistive networks. Okay, so please go over this lab manual. In today's lecture, we'll also go over how to find out your Thevenin and Norton equivalent circuits, and that's what we'll be doing for the pre-lab section of lab one. In the in-lab section, you will be asked to repeat what you have done in the pre-lab section and find out some of the input and output resistances, and I'll discuss more about the lab later on before your actual lab one starts on September 6th. So this is just to let you know that this has been already posted. So please keep an eye out for further announcement on this. But the first lab will start on September 6th. All right. So coming back to what we were discussing last week. So in Friday's lecture, we have looked into Ohm's law, we have looked into voltage and current division, we have looked into amplifiers, and we have looked into a few examples of how to solve for voltage gain or attenuation in this case, because this is just a passive network. There's no gain element, there's no amplifier over here. But later on, we had also looked into the equivalent circuit diagram of an amplifier, which was this. And then we also looked into what role does this source resistance or the input impedance of the amplifier, the output impedance of the amplifier, and the load resistance, what role does these resistances play in the overall gain of the circuit? That is something we had looked into in Friday's lecture. And you perhaps already can guess that even though this amplifier has an ideal gain of AV0, the overall gain in this circuit will not be AV0. And that's because there would be a voltage division at the input side between these two resistances. One is a source resistance. So this is a series resistance. That is a non-ideality of this voltage source. And then there is an input resistance of this amplifier, which comes in because of the input parasitics of the amplifier itself. Again, on the output side, there will be another voltage division between this RO and RL. RO is, of course, the non-ideality of the amplifier. So because amplifier is eventually also a voltage source in this case. So this is a dependent voltage source or a voltage controlled voltage source. What does this mean? That if you have an input voltage VI, your output voltage will be AV0 times that VI. So your input is a voltage, output is a voltage. So that's why this model is called a voltage controlled voltage source or a dependent voltage source. Okay. And because this is a voltage source, you of course understand that there would be a non-ideality that this voltage source will have a series resistance at the output. So that's where this RO comes from. Just like you had this series resistance of RS associated with your VS, you have this series resistance of RO associated with this AV0 times VI, this voltage source. Okay. And that resistance, when you consider the effect of that resistance along with the load resistance, you readily see that there is a voltage division going on over here. So that's why the overall gain of the amplifier would be a multiplication of three terms. One is the voltage division at the input, that is your VI over VS, and that would just be Rin over Rin plus Rs, right? Then the second term is the actual voltage gain of the amplifier, of the ideal amplifier. That's your AV0. And the third term is another voltage division that is going on at the output side. So that is RL divided by Rout plus RL. So you see that the overall voltage gain of the amplifier could be something lower than AV0. Why am I saying that it will be lower? Because again, these are passive circuits. It cannot increase your voltages or it cannot increase your power, right? So because this will just do a voltage division and the maximum voltage division you can have will be equal to 1. So you'll always have a gain of less than 1 for this voltage division and less than equal to 1. Let's say less than equal to 1 for this voltage division, as well as a less than equal to 1 term for this voltage division. So both of them will be less than equal to 1. Which means that the overall voltage gain that we'll have from this entire network will be something that will be lower than the original AV naught. Okay. And that's probably your homework question number 4 and 5 for homework 1. Okay, so next up, we'll be discussing a few theorems. Some of you already know about these theorems. These are called Thevenin's and Norton's. Let me bring this down as well. All right, the purpose of both Thevenin's theorem and Norton's theorem is that if you have a large circuitry consisting of many voltage sources, resistances, current sources, maybe even capacitors, inductors, all these different circuit components, what you can do is that you can simplify that entire complex circuit into something that is much, much simpler. So both Thevenin's theorem and Norton's theorem does that. Now, what's the difference between Thevenin's and Norton's? Thevenin's theorem talks about voltages. Norton's theorem talks about currents. So as you know that voltages and currents, we can just think about them as dual of each other, and they can be related using Ohm's law. In case of Thevenin's theorem, we'll be dealing with series voltage sources and resistances in series. In case of Norton's theorem, we'll be dealing with current sources and resistances in parallel. Okay, and we'll look into examples, so you don't have to remember all of that. But how to find out, for example, a Thevenin's equivalent circuit? For that, what you need to do is that let's say we have and we'll look into examples. Let's say we have a complex network that has a lot of voltage source. So let's say there is a voltage source over here, there is a resistance, maybe there is another voltage source connected over here for no reason, but I'm just drawing it right now just to make the system more complex. And then there may be multiple resistances, let's say in parallel or in series. So there could be something inside this black box, and you don't need to worry about that. What you need to worry about is that what's the equivalent voltage and what is the equivalent resistance does this black box present to you? Because at the output side, all you care about is that if you connect a load resistance here, let's say you just connect a load resistance of RL over here. All you care about is that what is the equivalent voltage and what is the equivalent resistance does this black box present to you? And that will be enough information for you to find out how much current is flowing through your RL or how much voltage will be developed across your RL. That's all you care about. And that's why even if you have a very complex network inside, it doesn't matter. So you need to know how to represent that in a more simplified way. So let me clear this for now. And let me tell you the general process of how to draw a Thevenin's equivalent circuit. So whatever circuit, complex circuit you have under the black box, the first step would be if you have a load resistance connected in the overall complex circuit, first disconnect it, because your job is to find out what's the equivalent circuit except for the load resistance. So don't connect any load resistance to the black box initially, like when you start the analysis. Your job is to find out the equivalent voltage that this black box present to you, and that equivalent voltage will be called the Thevenin voltage, V Thevenin, which is basically an open circuit voltage that this black box will present. Next, you want to find out what is the R Thevenin or the equivalent Thevenin resistance that this black box will present to you. So eventually you are trying to find out or trying to represent this black box using this network, which is a single voltage of V Thevenin and a single resistance of R Thevenin. And why would you want to do that? Because now if you just connect a load resistance over here, let's say I'm connecting an RL, this is a very simple voltage division example that you have already seen, right? That's what you are trying to get at. You are trying to represent this the complex network that is within this black box into something that contains only V Thevenin and R Thevenin. So if you do that, first step is that remove this RL. You don't need to consider RL initially because you care about what's inside this black box. So all you care about is V Thevenin and R Thevenin. V Thevenin is just the open circuit voltage that you are trying to look at. So for example, if you try to measure the voltage looking at these two terminals, that is basically this V Thevenin, right? Similarly, how to find out R Thevenin? To find out RThevenin, there are a couple of methods that people usually follow. First thing is that to find RThevenin is, because you have access to only the right hand side, you can only connect or disconnect something on the right hand side. You cannot do anything else within the black box, right? So if you want to find out what is RThevenin, you can connect a voltage source or a current source. So for example, here we are connecting a voltage source. Here we are connecting a current source. So you are trying to connect the voltage source or current source on the right hand side. But before doing that, you need to kill all the independent voltage sources that are inside this black box. What does it mean by killing all the independent sources? Is that if you have a voltage source, just short it out. So instead of having this voltage source, just short these two terminals. And then you place a voltage source over here. An arbitrary voltage source, let's call it Vx. Okay, or V test as it is mentioned here. So Vx is basically equal to your V test. So this is an arbitrary voltage source. And what you are trying to do here is with this V test, or in this case, we are connecting an I test. So let's consider the V test first, that if you have a V test connected, there would be a current flow inside this loop, right? And you can measure how much current is going into this loop. So when you have this V test connected, and you can, let's assume that you can figure out what is the amount of I test that will be going into this black box, then you'll know that your RThevenin is basically V test over I test. So your RThevenin is basically your V test over I test. So if you have a voltage source over here and you measure how much current is going into your black box, the ratio of those two will be the Thevenin resistance. And that's something you can figure out from this particular drawing that I have done on the right hand side, right? That you first kill all the independent voltage sources and then do this. If you had this voltage source present when you are connecting this V test, let's say you have this voltage source present, then that equation will not hold true, right? You already know that Kirchhoff's voltage law states that the overall total voltage, the summation of all the voltages in the loop will be equal to 0. And as soon as you introduce more voltage sources over here, your equation will be something different according to KVL. So first task is to kill all the independent voltage sources. That means short them out. Similarly, if you had an independent current source, the way to kill it is to open it. Because when you open circuit, something current cannot flow. That's how you kill a current source. So you have to open circuit the current sources. Similarly, how to kill the voltage source is that you short it out. If you short two terminals of a voltage source, there is no voltage developed across it, right? Because if it is a short, the voltage developed is 0 across that short. So that's the general process that you will follow to find out the Thevenin voltage and the Thevenin current. And this is just one way that I mentioned that you can find out the Thevenin equivalent resistance. That is by placing a V test at the output. Before that, kill all the independent voltage sources or current sources. Place this V test, measure how much I test is going in, and your Thevenin equivalent resistance will be V test over I test. Similarly, you can do the dual of it. That you connect a I test and a current source at the output, measure how much voltage is it developing. Because internally you have shorted this voltage, the voltage V test that it developed across I test will be I test times the Thevenin equivalent resistance. So again, your equation will remain the same. R Thevenin will be V test over I test. There is another way to find out what is your R Thevenin. That is, first, so you had this black box, right? And inside this black box, what do you have? Inside this black box, you effectively have a Thevenin equivalent resistance, and you have a Thevenin equivalent voltage, that is V Thevenin. That's a simplified version of whatever you have inside this black box. Now, to find out R Thevenin, what you can do is that you can measure the voltage in an open circuit scenario, that you measure the voltage, open circuit voltage at these two nodes, and that voltage will be same as this V Thevenin. Right? When this is open circuit, when this output is open circuit, what is the voltage developed across this? Because this is open circuit, there would be no current flow. If there is no current flow, there is no voltage drop across this resistance. And if there is no voltage drop across this resistance, the full voltage of Thevenin is available at your output. So your open circuit voltage is the Thevenin equivalent voltage. If you short this output, let's say you directly put a short over here, you just connect it with a wire, these two terminals, then there will be a current flow through this. What would be that amount of current? That amount of current would be Thevenin over Thevenin. So that's your I short circuit. And your open circuit was Thevenin. So this was your numerator was Thevenin, and your denominator is I short circuit, which is Thevenin over Thevenin. So this is Thevenin over Thevenin. So as you see now, your numerator and denominator, this Thevenin term will get cancelled out. The Thevenin will go into the numerator. So of course, that's what you are trying to find out. So this is another way to find out the Thevenin, that you calculate the V open circuit, you calculate the I short circuit, and take a ratio of those two. So there are three different ways you can do the same thing. And that's something interesting about circuit analysis, that there are multiple ways to come to the same conclusion and the same answer. And every method that you follow, if it is logical, it is correct. It just has to be logical. But there can be hundreds of different methods to come to the same conclusion. All right, so let's look at an example of the Thevenin's equivalent circuit. So let's say this is the network you're trying to look at. This is still a simple network. It's not very complex, but let's try to look at it as an example. So you have a voltage source V0 over here. You have two resistances R1 and R2. And this is the output port you are trying to look at. So this is called a port, which is basically a combination of two terminals. So you have let's say a positive terminal. This one is a positive terminal, and this one is a negative terminal. So a positive terminal and negative terminal together, we'll call it a port. Now, what is your black box as compared to the previous slide? This is your black box. What is there inside? You have this V0, R1, and R2, but we want to find out what is the Thevenin equivalent voltage and the Thevenin equivalent resistance inside this black box. So how to find that out? First thing you should do is that you want to find out what's the equivalent voltage available at this port. So available between these two terminals, the positive terminal and the negative terminal. And the voltage that is available, the open circuit voltage that is available, that is your Thevenin voltage, correct? According to this. So whatever voltage you have available in the open circuit case, so when you did not have this output shorted, in the open circuit case, whatever voltage you have available, that's your Thevenin voltage. If this is an open circuit, if you don't connect anything at the output, what is the open circuit voltage that you developed across this port? That is basically a voltage division between this R1 and R2, and whatever voltage is available across this R2, right? The voltage available across R2 is the voltage available at the output. What is the voltage available across R2? V0 times R2 divided by R1 plus R2. So that's application of your voltage division equations that we have learned in the earlier lecture. So that becomes your Thevenin equivalent voltage for this circuit. The open circuit voltage is the Thevenin equivalent voltage for this circuit. How to find out the Thevenin equivalent resistance? You need to first kill the voltage sources, the original independent voltage sources that are inside this black box. So you'll short this out. And you look at what's the effective resistance looking into this port. One way to do that is to put a voltage source over here, which let's say you put Vx or a Vtest voltage source and try to measure how much current is going. But we have already looked into, so that's your nodal analysis that you have learned in 3111. But we already know from the previous two lectures that how to find out the equivalent resistance looking into this port. What do you see looking into this port from the right hand side? You see a resistance R2 and you see a resistance R1 in parallel because you have shorted this voltage source out. So the resistance that you see looking from the right hand side into this port is basically R1 in parallel with R2, and that's your Thevenin equivalent resistance. Okay, so this is the Thevenin equivalent circuit of what you have seen in the on the top. That you find out the open circuit voltage, that becomes your Thevenin equivalent voltage. Then you short all the independent voltage sources or open all the independent current sources inside your black box and find out how much resistance are you seeing looking from the right hand side, looking from the load. And that gives you the Thevenin equivalent resistance. Now, if you solve this circuit, it will be exactly same as solving this a little bit complex circuit. Let's look at an example, and we are trying to look at an audio microphone system, for example, let's say. The input impedance or the input resistance of an audio amplifier is usually 50 kilo ohm. So let's say you are connecting an audio amplifier on the right hand side, but on your left hand side you have a microphone system. So your audio amplifier's input impedance or input resistance is this 50 kilo ohms. On the left hand side, whatever you have is basically a voltage that you are trying to propagate to the input of your audio amplifier. And this network has this kind of a resistive division. So you have R1 of 100 kilo ohm, you have R2 of 30 kilo ohms, and R3 of 10 kilo ohms. And let's say your input voltage or the input to the microphone is about 10 millivolt. That's the amount of voltage you generate at the microphone when you speak into it. So 10 millivolt will probably not do anything. So that's why you need an amplifier that's on the right hand side. But again, we are not looking into the amplifier. We just want to look at the input resistance of the amplifier. And keep in mind, remember that we talked about the input resistance of an amplifier in the previous lecture, which is a non-ideality. Ideally, it should have been infinite. This is the input resistance in this case, the 50 kilo ohm input resistance that you see for the amplifier. And you want to find out how much voltage is available at the amplifier's input if your input voltage is 10 millivolts. And we want to solve this using Thevenin's theorem. Again, you can solve it using Thevenin, you can solve it using Norton's, you can solve it using the basic theorems or the basic theories that you have learned for voltage division and current division, and everything will lead to the same result if you're doing it correctly. So, but we want to learn how to apply the Thevenin's theorem here. So we'll look at the solution method. But keep in mind, in the exam, you can solve the problems using any method, and any method is fine. Whatever you find more suitable or whatever you find more intuitive to you, just apply that method. And that's what is important. It's important to know that these methods exist, but depending on how you think about the problem, one method could be much simpler to apply for you than the other method. And it's perfectly fine for this particular class. All right. So how do you solve this? So first thing is that disconnect the load. The load does not matter. The load could be anything else. Still, your Thevenin equivalent circuit should remain same. The Thevenin equivalent circuit should not depend on the load, because again, what you are trying to design is basically a black box with a Thevenin and Thevenin, and you can connect any load to it. That's your goal. So you are just trying to characterize the black box, and the load is not a part of the black box. So that's why first thing you'll do is that you'll disconnect the load. And then you'll find the Thevenin equivalent for the remaining circuit. You'll reconnect the load and find how much load voltage you are developing. Those are your 4 steps. So, of course, if you disconnect the load, this becomes your black box that you have a V mile, you have this resistive network, you need to find out what is the Thevenin equivalent voltage and Thevenin equivalent resistance, and then connect the load back. So, to find the equivalent Thevenin, first step is set the voltage source to 0. So you short this voltage source at the input. There was this voltage source, you're just shorting it out to kill it. Why? Because you are trying to look at it from the right hand side, and you're trying to find out what's the equivalent resistance. And now you can already find out what is the equivalent resistance. That would be R3 plus R1 in parallel with R2, because now R2 is in parallel with this R1, and then you just add R4 to it. R4 comes in series. So when you're looking into these 2 terminals, let's say this is your terminal 1 and terminal 2, and you traverse it in this way, that you go through R3, then you have a parallel combination of R1 and R2, and then in series you have R4, and that's how you reach this second terminal. So your overall Thevenin resistance is R3 plus R1 in parallel with R2 plus R4, and you can calculate how much that would be, and that comes out to be 43 kilo ohms. So your R Thevenin is 43 kilo ohms. What is your V Thevenin? That's your open circuit voltage. And again, you will analyze this circuit under no load condition. Why? Because the load is not part of your black box. You are only interested in characterizing the black box. The voltage across this port terminal in the open circuit condition, that would be your V Thevenin. How you can solve this? If you have this voltage source and if you have this series of resistances, the current will only flow in this inner loop, right? There will be no current flow here through this resistance or through this resistance. There is no current flow here. There is no current flow here. Why? Because this part is open circuited. If the right hand side is open circuited, there cannot be any current flow like that, right? So there is no current flow through the resistances R3 and R4. There is no current flow on the right hand side of this circuit. There is only current flow in the inner loop, and that current flow is how much? That is this 10 millivolt divided by R1 plus R2. How much voltage do you develop across R2? The voltage that you develop across R2 is V mic times R2 divided by R1 plus R2. That's the voltage you developed across these 2 points. And that would be the same voltage that you have at these 2 points because there is no current flow in this loop. So the voltage developed across R2 is your output Thevenin voltage. And that you can calculate through the theory of voltage division, and that would become 2.3 millivolts. Okay, so your Thevenin equivalent voltage is 2.3 millivolts, and Thevenin equivalent current is 43 kilo ohms. To find out how much load voltage you will have, just connect back the load. The load was 50 kilo ohms, and now you can do a simple voltage division and find out what would be your V load. V load will be the voltage division between the Thevenin resistance and the load resistance. And because this is 43 and 50, it's almost a 1:1 division. So if you had this 2.3 millivolt input, you'll see that eventually, like the output of that voltage division becomes this. Right? So 50 kilo ohm divided by this 93 kilo ohms. I think there is a typo. Let me correct this. So this should be around 1 millivolt or so. So the final answer should be something else. Let me correct that. But eventually it's 2.3 millivolt multiplied with 50 divided by 93. So that's the example of Thevenin's theorem. I think you already know about Norton's theorem as well from your 31111. But the Norton theorem is just the dual of your Thevenin. There, instead of modeling the black box using a voltage source and a series resistance, you'll model the black box using a current source and a parallel resistance. So I can draw this out. So basically, if you had this voltage source and a series resistance, and we are calling it the Thevenin voltage and the Thevenin equivalent Thevenin resistance. That's what we learned in the last few slides, right? The Norton equivalent circuit for this would be I Norton in parallel with a R Norton. And what is the relation between these two circuits? The relation is that the R Thevenin is equal to R Norton. So R Thevenin is exactly equal to Rn, and your In is basically your V Thevenin over R Thevenin. That's the value of your Norton equivalent current, which is again equal to V Thevenin over Rn, because Rn and R Thevenin are equal. So why I'm saying that these two are equivalent? Again, if you look into these 2 points, what is the voltage that you develop across these 2 points? That should be equal to this I Norton multiplied with R Norton, right? Because there is a current flow in this loop. The open circuit voltage that you develop over here would be a multiplication of In and Rn and that would be equal to your Thevenin. That you can also find out from this equation, that your IN was Thevenin over RN. So Thevenin is equal to IN times RN. So the Norton circuit and the Thevenin circuit are just duals of each other. It's just two sides of a coin. It's two different ways of looking at the same thing. It's not anything different. It's just the dual equivalent circuit of what we just learned now. All right. Now there are a few limitations of Thevenins and Nortons. First of all, that these are only applicable to resistors, capacitors, voltage sources, current sources, etc. But they are not applicable for more complex or higher order circuits such as diodes and transistors that we'll learn later in this course. And that's why the Thevenin and Norton equivalency is usually applied when you have a linear network that consists of resistors, capacitors, inductors, voltages, and current sources. That's it. You don't apply it to more complex networks that we'll be learning towards the later part of this course. And that's why I guess 311 had considered the Thevenin and Norton theorem as one of the more fundamental units, but here we are just going over it. But when we start discussing diodes and transistors, we'll not look into Thevenin or Norton equivalent circuits anymore. But the more fundamental theories, that is voltage division, current division, amplification, things that you have learned in the previous lecture, those will still be applicable. All right. Any questions over here? So next, I had also uploaded, so if you look into Canvas, in lecture 2 notes, this is, we just finished whatever was left for lecture 2, and there are a few practice problems and notes given at the end of that class, so which I'm showing over here. Again, it's just a summary of what we have learned in terms of voltage division, current division, Thevenin's theorem, Norton's theorem, and a few specific examples. So just go over this. This will help you in solving the homework 1 in a better way if you haven't already looked into this. So today we are mostly going to look into amplifiers in a little bit more detail. Now, we have already looked into some of this in the previous lecture, and you already know that, okay, if I have an amplifier, if I have an ideal amplifier, the job of this ideal amplifier is that if you have an input voltage, Vin, the job of this to create an output voltage, which is an amplified version of the input voltage. Now, this is true for a voltage amplifier. There could be few other types of amplifiers, for example, current amplifiers. The job of a current amplifier is to amplify the current. The job of a transconductance amplifier, so just like there are voltages and currents, the ratio of voltage over current is called resistance, right? Or in a more generic term, this is called impedance. So what impedance means is that resistance is invariant of frequency. If you have a resistance R, which is V over I, that resistance is not varying with frequency. But there could be capacitive components, there could be inductive components which vary with frequency. So resistance is not a function of frequency, but capacitance and inductance are, or the impedance due to capacitances and inductances are a function of frequency. So if you know about capacitance, the impedance of a capacitance is 1 upon j omega c. Right? So this is dependent on omega, which is the frequency, the angular frequency. Similarly, the impedance of an inductor is j times omega times L, j omega L. That is again dependent on frequency. So impedance is a more generic overarching term than resistance. So resistance only means voltage over current. Impedance means that you can have a physical resistor, you can have capacitors or inductors, but the overall impedance, what is the overall voltage over current in that circuit, that is given as impedance, which becomes a function of frequency because inductors and capacitors are a function of frequency. So impedance is a more generic term as compared to resistance. But in a more simplified form, they mean the same thing, that when you don't think about frequency at all. So why I'm saying all this? Because the amplifier could be a voltage amplifier, that your input and output could be both voltages. It could be a current amplifier, that your input and output are both currents. So let me draw this. So you can draw this 4-quadrant. This is called a 4-quadrant graph. that you have a x-axis in both positive and negative direction, you have a y-axis in both positive and negative, and you create 4 quadrants for this. So you have a 4-quadrant graph. Now let's say the x-axis represents the input. Let's say x-axis is your input and y-axis is your output. So your x-axis could be voltage or current. Your y-axis could also be voltage or current. When your input is a voltage, output is a voltage, you have this voltage amplifier, and that amplification gain you represent as AV. When your input is a current and your output is a current, you will represent the amplified gain as AI. The other 2 cases are a little bit more interesting, where, for example, in this quadrant, your input is a current, output is a voltage. So this is called a trans-impedance amplifier. So you can represent the gain as AZ, because most of the times the impedance is given by the notation of Z. So in this case, your output is a voltage, your input is a current, your notation is an amplification in the trans-impedance. Because and why I am calling it a trans-impedance? Because your output is voltage, your input is current. The ratio of your output quantity to your input quantity, that's what you're interested in. That's what you're transferring an input current to an output voltage. So your transfer function is basically an impedance. You're converting a current to a voltage. That's why this is called a trans-impedance. Similarly, the other case, when your input is a voltage, output is a current, you're transferring a voltage to a current. If your input is a voltage, your output is a current, you're transferring a voltage to a current. That is called transconductance. So you're transferring using a conductance transfer function. So this is a transconductance amplifier. So there could be 4 different types of amplifiers. One is a voltage amplifier, one is a current amplifier, one is a trans-impedance amplifier, and the other one is a transconductance amplifier. So keep in mind that there could be 4 different types of amplifiers going into the future lectures in this course. But for now, let's just keep things simple. Let's just think about a voltage amplifier. Your input is a voltage, output is a voltage. Now, if your input is a voltage, output is a voltage, you can represent this using this kind of a voltage transfer characteristics. So this is called a VTC, or a voltage transfer characteristic, where you're showing that as you're changing your input voltage, how does your output voltage vary? And we'll discuss why this VTC curve looks like this, maybe in 2 more slides. But right now, let's just assume that the VTC curve looks like this. That initially you do not see any, as you are increasing the input voltage from 0 to a high value, your output voltage remains high. Output voltage remains a high value for some time when you are increasing your input voltage. Then suddenly it starts to drop, and then eventually it becomes very close to 0. So let's just assume this is how your VTC looks like for a voltage amplifier. And we'll discuss why it looks like this in a couple of slides. Right now, just assume that this is true. Now, what is the gain? What is the gain? The gain is basically the output, and as I said, that when you are talking about gain, it's always the AC gain. An amplifier never gives you DC gain. So never expect that if you have a DC input voltage, your amplifier will amplify the DC to an output voltage which is higher than the input. Don't expect that. That's not the amplifier's job. That is the job of something called a DC to DC converter. The amplifier's job is to amplify the input AC voltage. If you have an input AC voltage of, let's say, a swing of 5 millivolts, the amplifier's job is to make it 50 millivolts if it has a gain of 10. But don't expect the amplifier to increase the DC voltages. So if we agree to that point, that the amplifier's job is to amplify AC voltages, and how do you mathematically represent AC voltages? You represent AC voltages with derivatives, right? So if you have a small change in the input voltage, you call it a del V in. If you have a small change in the output voltage, you call it a del V out. The ratio of those two is your amplifier's gain. So if you have output quantity of V out, input quantity of V in, del V out divided by del V in, or the derivative of V out with respect to V in, that's your amplifier's AC gain. Mathematically, this is how you represent gain. So if we agree to that, in this curve, what is del V out over del V in? What is the derivative of V out over V in? That's the slope of this curve. So the slope of this curve, the VTC, slope of the voltage transfer characteristic, is basically your gain. So as you can see that in this region, the slope is 0. Because your output does not change even if your input is changing. So your numerator is 0, your denominator is a non-zero quantity. So the slope or the gain of the circuit in this region is 0. Again, the slope or gain of the circuit in this region is 0. You only have gain in this middle region. Okay. What does that mean? That means that if you apply a small AC voltage, where that AC voltage swing, let's just assume that this is 0 to 100 volts. I'm just exaggerating things, but let's just assume that this is 0 to 100 volts on the left axis, y-axis, and 0 to 100 volts in the x-axis. For the first 10 units, you don't see any change in the V out. You don't see any kind of gain. Where do you see the gain? When both the input and output voltages are near the 50% points. And again, when your input voltage reaches to the 100% point, that is, it reaches its maximum voltage, you don't see any gain again. So we talked about two very important things here, even if we didn't realize it. First, the amplifier amplifies only AC inputs. Right? It does not amplify DC inputs. But the DC voltage has to be near the middle of its voltage transfer characteristic so that you can expect gain out of it. If your DC point is here, let's say your sine wave or the input voltage that you are applying to the amplifier is between, again, we are just assuming that this is, let's divide this between 0 to 100, the y-axis as well as the x-axis between 0 to 100. If your voltage swing is in between, let's say, 3 and 5, you do not see any change in the output. When your input swing is between 97 and 99, again, you do not see any change in the output. But if your input swing is between 49 and 51, you see a huge change in the output. So this is called biasing. So your amplifier or your transistors need to be biased near the middle of their range so that they can operate correctly. So this is called a DC bias. So again, as I said, that these are two different things, but both are very important. The DC needs to be placed at a point where it is biased correctly, where you are in the middle of this VTC. So the DC biasing just ensures that you are not over here and you are not over here. That's it. DC biasing does not mean anything else. It just means that you need to be over here. And how much gain do you expect from the amplifier? That's basically the slope of this curve, VTC curve. And that slope can be different in different amplifiers. If you design a very good amplifier with a high amount of gain, the slope will be high. If you do not have that much amount of gain, the slope will be low. So that's the gain of the amplifier. That has nothing to do with the biasing. The biasing has everything to do with whether you will expect a gain out of that amplifier or not. Even if ideally your amplifier has a gain of 100, you may not see any gain if you're biasing it at this point or biasing it at this point. So what does biasing mean? It's placing, so for example, at your input, you have a sine wave. And this is AC, so this is a small sine wave. And let's just assume that the swing, the amplitude of this sine wave is just 1 millivolt. Okay. Biasing signifies that what is this average DC point? What is the DC point of this sine wave? If the DC point is near this 0 voltage, or very high voltage, your amplifier will not work. The DC voltage, let's say your ground is 0, and let's say your VDD is 1 volt. In that case, the DC voltage needs to be very close to half of the power rail, which is the difference between this 1 volt and 0 volt, that is 1 volt, and half of that is 0.5 volt. So if your DC point at the input is near 0.5 volt, then you are at this point. If your DC voltage at your input is 0 volt, then you are at this point. If your DC voltage of your input is at 1 volt, then you are at this point. The amplifier will not work if your DC voltage is too low or too high. It will only work if your DC voltage is in the middle. Okay, any questions? So this is a very important concept when you want to learn about electronics. And yes, questions? Yes, so where you have the question is that I said that the amplifier does not amplify DC voltage, but amplifier needs a DC voltage to work. And that DC voltage that it needs is called a bias voltage. So it does not amplify that DC voltage, but it needs a DC voltage so that it can work. And why do you have the need for the DC voltage? Because in your voltage transfer characteristic, that is this plot, in your voltage transfer characteristic, if your DC voltage is too low, the amplifier will not work because the slope is 0. If the DC voltage is too high, the amplifier will not work because the slope is 0. Only in the middle, if you place your DC voltage in the middle, only then the amplifier will work and you can expect a gain out of it. So biasing and amplification are two different concepts. Biasing only means that you are placing the DC point of your input in a region where you can expect the gain out of it, expect the correct gain out of it. But the amplifier cannot do everything that you, so for example, you cannot expect that, okay, I have a 1 millivolt input, the amplifier output will be 100 because the data sheet says so. It does not work like that. You need to place your input. It can be a 1 millivolt input, but you need to place your input, the DC point of your input, near half of the VDD range or near, so if it has a VDD and a VSS, so let's say in some amplifiers you'll have a VDD of plus 5 volt and a VSS of minus 5 volt. There the middle is near 0. Then you can have your input DC point at 0. If your VDD is, let's say, plus 5 and if your VSS is minus 5. Okay. So the main concept is that you have to place your input DC point near to the middle of the VDD and VSS, the average of your VDD and VSS. Questions? Yeah. No. No and yes. So if you're saying that if you have a very large input, right? So that is the case you are referring to. Then it may change a little bit, but if your DC input is near to the half of your power rails or the average of your power rails, that's the best you can do. You cannot do anything better than that in most cases. So if you're placing it at 0.5 of the VDD or the average of the VDD and VSS, that's probably the best we can do. So we'll start from this in the next lecture, but keep this in mind that this is the most important takeaway that you can take from this class as well as probably this entire course, that the amplifier can amplify only if you provide the correct DC bias.
Yeah. Okay, so okay, we learned about gain. Yeah. So, okay. I was feeling I thought gain.
This is it is what? Because this you have to overthink. The gain is what is an Like DC is no changing to the output. Okay. AC is a small change in the output. How do you represent a small change in the output? The del V. I was looking at the line. How do you represent a small change in the input? A del VC. The ratio of del V out or del V, that's your real definition of that. It's just V out over V does not mean that AC is alive. It's exactly right. Del V out over del V means an AC, which is basically a derivative.
Okay, so these are DC, right?
These are DC, but yeah, I mean this may sound confusing, but in all the books and all the material that you see, you'll always see a V and V out. That says like your amplifier input is your amplifier output is V out. It never says that this is an AC output.
Okay.
That's the gap. Like when I was a student, when I was learning circuits on the exact same question like that. Is it DC or is it an AC?
Okay, we're saying it's DC.
When you think about the amplifiers function, but to make it work, there also needs to be a DC that sets the AC near this point. So effectively, this is a combination of DC and AC.
Okay.
The DC is basically this half ADB point, correct? And the AC is a small swing over that half ADB. The job of the amplifier is to amplify that small AC, but it needs a DC to make sure that it can do what you want it to do.
Okay. All right, thank you.
The DC point is in the middle. So the amplifier needs both the DC and the AC. It amplifies the AC. It does not amplify the DC, but it needs the DC to operate. So we will look into like more details why it needs the DC. But I think it will be more clear as we progress throughout the. But right now, keep in mind that it needs a DC. If you don't provide a DC, it will not work. Right? But it does not amplify the DC. It amplifies only the AC. And it's a bit confusing. I know that as I said to the other person that when I was taking circuits one, when I was an undergrad, I had the exact same question and the exact same confusion. What the hell is happening over here? Right? That is what does it amplify? Why does it need a DC? So I'll ensure that I try to explain it again and again throughout the course wherever it is relevant. But the books do not talk about it because they just talk about an input voltage and so an output voltage says that okay, it is amplified. But it does not work like that. You need to apply a DC bias, then provide on top of the DC bias, you need to provide a small input voltage, then only you will get the output. Both the bias and the input needs to be provided. The DC bias and the AC input needs to be provided for the amplifier. If you only provide the DC bias and no AC input, your output will not have any AC contribution. Right? So the job of the amplifier is to amplify the AC. But for that, because of the VTC that we saw, the voltage transfer characteristic that we saw, and I'll explain that again, that why the VTC looks like this. Because of that, we saw that whether the input voltage is very small, or the DC is very small, or the DC is very large, it does not work. The DC needs to be in the middle of your VTC and DSA. So you might see in the lab that some components, even if you don't apply a DC bias, that will work. But those are components where you have a VDD of let's say plus 3.3 volt and a DSS of minus 3.3 volt. So the average of that is near 0. And the DC bias means that the average or the DC point of your input has to be the average of your VDD and DSS. So those components which have a VDD and a DSS of plus 5 and minus 5 or plus 3.3 and minus 3.3, those components will work if you have a if you don't even provide an input DC voltage, and if you have your input DC voltage equal to 0. But that's just an effect of the fact that your VDD was plus something, your VSS was minus something, and the average is 0. That's why it works. It does not mean that it can work with 0. So again, like as we make more progress in the class, I think some of these concepts will become clearer. But for now, if you have this doubt and confusion in your mind that okay, there is a AC part, there is a DC part, and I need to make both of them, you are in the right direction. You'll learn more and you'll figure it out that how to make both of them. But if you assume that okay, I just provide an AC input, I expect an AC output, that will never happen. As long as you have this doubt in your mind that I need to do something extra, you are in the correct track. Okay, and you learn about this, what extra we need to do to make sure that amplifier works. Thank you. Sure.
I just wanted to ask about one more question. So in this case, we have the current going the other way. So would the 8 end up being negative?
Perfect. Perfect.
Yes.
I'll talk about this in the next lecture.
Okay. Yeah. And then in terms of biasing, are we going to go over like more so than the theory, like practically how to do that with like an op-amp chip? Or
that will be the lab. In the lab. So
in one case for Audio Engineering Society, we're trying to build a guitar amplifier.
Right. I think you talked to me.
Is there any way you possibly give me some resources for biasing?
Sure. And I'll give you some resources, but talk to one of the UPIs, Norton.
Okay.
So he has been here for like I think this is his final senior year, and he has designed all these circuits in the past.
Okay.
So he will be able to guide you exactly that which component to buy, how to place it, and all this.
Okay.
If you want to talk to him, but he's I think all the details are provided in Canvas.
Thank you.
So RMS voltage is actually one way to represent the AC swing. So maybe I can draw something on the board. This is the AC that we are talking about. And then now you expect an amplified AC, right? That's the amplified. Now, what you talk about is the RMS. That is a way to represent the swing of this AC. Okay? That if it is a larger swing, your RMS voltage will be higher, which is 0.707 times of the peak. So you can represent this as RMS or peak to peak, whatever way you want. Right? I mean, then again, the signal does not. The amplitude is this much. The peak to peak voltage is this much, and the RMS is 0.707 times of the amplitude. So it's just 3 different ways of representing the same thing, but and you can probably think about it as 3 different units. So you have for temperature, you have units of centigrade as well as Fahrenheit. Right? The temperature does not change; it would represent it in different units. So again, these are just different ways of representing the same signal. Now, input can be like this: the small signal AC. The output is a large signal AC. So small signal means the input is small. Large signal means that it is large. Like that's as simple as that. Now, important thing is that we know about the swing. What should be the average? So if this is 1 millivolt, is it 1 millivolt across 500 millivolts? Or is it 1 millivolt across 0 millivolts? Like, what is this average level? Is it -1 to +1, or is it 499 to 500? If your VDD is 1 volt and ground is 0. That's the question. Right? The RMS is something with which you can represent the AC. So it could be, as I said, that RMS could be something with which you represent the AC signal. The peak amplitude is something with which you represent the AC signal. The peak to peak is something with which you represent the AC signal. All of them talk about the same. The DC should be different, right? So again, the AC signal could be 1 millivolt peak. It could be 2 millivolt peak to peak. It could be 0.707 millivolt RMS. All of them will represent the same signal, but it does not say anything about the DC. The DC is something that we are interested in. That's the bias we are talking about. That is this 1 millivolt on the 2 sides of 500 millivolt, or is it on the 2 sides of 0 millivolt, or is it on the 2 sides of 700 millivolt? We don't know about that, but that's very important for this amplifier to work. Maybe let's take the question outside because there is another class.